All right, so when we were talking about cryptography, we said that we are going to use these algorithms on the internet via TLS. Okay, so let's briefly see how this works. So TLS stands for Transport Layer Security. Widely deployed security protocol above the transport layer, supported by almost all browsers, web servers like HTTPS, which uses port 443. Okay, so we say that transport layer security, but actually it is implemented in the application layer. But for the user perspective, it looks like it is in the transport layer. Okay, so it provides confidentiality via symmetric encryption like AES and ChaCha, integrity via cryptographic hashing. Here, not like the book says, it is not MD5 or SHA-1, but it is SHA-2. Authentication via public key cryptography, and we already seen all of these topics. Okay. So history is as follows: early research implementation, secure network programming, secure sockets, secure socket layer SSL, deprecated in 2015. Now we have TLS 1.3 since 2018. Okay, so when we have this kind of updates, we are actually eliminating broken cryptographic algorithms. But nowadays, I think around 70% of the whole internet uses TLS 1.3. But probably they have backward compatibility, so you may sometimes force them saying that you don't have TLS 1.3, and you can even force them to use TLS 1.0 if they haven't correctly configured their server. So if you can perform such a downgrade attack, you can force them to use RC4, which is badly broken. Okay, so you should actually configure your server so that you shouldn't accept anything below TLS 1.2, but you should also doesn't allow them to use broken algorithms like MD5, SHA-1, or RC4 and so on. So the book here tries to explain TLS by dividing into pieces. So it says that let's build a toy TLS called t-tls to see what is needed. So we have seen the pieces already. Handshake, Alice, Bob use their certificates, private keys to authenticate each other, exchange or create shared secrets. Key derivation, Alice, Bob use shared secret to derive set of keys. Data transfer, stream data transfer, data as a series of records, not just one-time transactions, because we are going to divide them into pieces. Probably we will number them. Connection closure, special message to securely close the connection. So recall that we had three-way handshake and TCP. Then we can put our TLS here, our toy example. You can start with t-tls hello, and the person can send their public key certificate, right? So then you create a master secret key, encrypt it with Bob's private key. So Bob actually encrypts and sends it to Alice. Then Alice can decrypt it by using Bob's public key. So let's read the slides. Bob establishes TCP connection with Alice. Bob verifies that Alice is really Alice. Bob sends Alice a master secret key, MS, used to generate all other keys for TLS session. Potential issues, 3 runtime trips here, right? Before client can start receiving data, including TCP handshake, right? So there are many messages here. So good thing with TLS 1.3 is that we don't have this many messages to send and receive. Okay. So cryptographic keys in this toy example. So it is considered bad to use same key for more than one cryptographic function. So using the same secret key, for instance, for both AES encryption, but then also using it, for instance, like in HMAC, you would be using the same plaintext with same secret key, but 2 different algorithms. So in the past, we have seen many scenarios where this actually leaked more information, okay? This is why we actually want people to use different keys for different purposes. So here we want to use different key for message authentication and different key for encryption. So this is why we have 4 keys, 2 for message authentication and encryption, the other one for the client and one for the server. Okay. Key is derived from key derivation function, KDF. Takes master secret and possibly some additional random data to create new keys. Recall our password-based key derivation functions. So here it is similar, but does not depend on a password. Okay. So TCP provides data byte stream abstraction. Question: can we encrypt data in stream as written into TCP socket? Answer is: where would Mac go? If at the end, no message integrity until all data received and connection closed. Solution: break stream in series of records. Each client-to-server record carries a MAC created using MC. This was the secret key. Receiver can act on each record as it arrives, right? Okay, so let me go back. MC was the MAC key for data sent from client to server. Okay, so here you put a length of data, then the MAC. Okay, so book goes in this way, then it will show you this idea is not okay and will add something more. So t-tls record encrypted using symmetric key KC passed to TCP. So instead of sending your payload in as a plain text, now we have the encrypted version of it. Okay. So if we go back to our message authentication codes lecture, this is like MAC then encrypt method, right? First you calculate the MAC, then you provide the encryption. Okay. So possible attacks on data stream: reordering. Man in the middle intercept TCP segments and reorders, manipulating the sequence numbers as in unencrypted TCP header. So this is one way of attacking it. Replay attack, keep sending the same message. Solutions: use TLS sequence numbers. So this way they cannot reorder it, because in the TLS sequence number you will put inside next to payload and then encrypt it. And this way, they will not be able to change it. This way, you provide integrity. And to avoid replay attack, you use nonce, because if you receive the same message with the same nonce, you will actually drop the packet, because recall that nonce is a value that is only used once. Okay, so truncation attack: attacker forges TCP connection close segment. So this way, while you are still communicating, somebody forges a TCP connection close message. So the server actually cannot receive the remaining part of the TLS part, right? Because somebody claims that the connection is closed, so you believe it. One or both sides think there is less data than there actually is because of this attack. Solution: record types with one type for closure. Type, for instance, type 0 for data, type 1 for close, but put it inside, then encrypt it, so this way they cannot modify this, right? Make now computing using data, type, and sequence number. Okay. TLS provides an API that any application can use. So an HTTP view of TLS is as follows. So you have at the application layer, you have HTTP, but after that, when you're sending your data to transport layer, actually you use TLS. This is why from the application point of view, you see it as a transport layer security, but it actually happens at the application layer. So this is why we call it HTTP2 over TCP. And nowadays, we already mentioned QUIC. So QUIC actually incorporates TLS over UDP, right? This is referred to as HTTP3, which we already mentioned, okay? So yes, which ciphers we are allowed to use? This is called cipher suite. Algorithms that can be used for key generation, encryption, MAC, digital signature. So in TLS 1.3, we have less ciphers compared to TLS 1.2, okay? Only 5 choices rather than 37 choices. Here the sentence looks suspicious. It says requires Diffie-Hellman DH for key exchange rather than DH or RSA. So, what you might be confused here, because it says that you should use the Diffie-Hellman instead of Diffie-Hellman, right? So again, there is a typo here. Actually, here you still can use Diffie-Hellman key exchange with RSA and so on. But the change from TLS 1.2 and to 1.3 is that now you have to provide forward secrecy. This means that whenever you are actually using Diffie-Hellman, the values you create for that instance should not be related to your next Diffie-Hellman key exchange, okay? Because if you kind of combine them, for instance, let me give a very basic example. In the first Diffie-Hellman key exchange, you randomly generate a number, right? Let's say A. So in your next Diffie-Hellman key exchange, if you use A plus 1, so at some point in the past, somebody, if can break your Diffie-Hellman key exchange and captures A, this would mean that they would capture every Diffie-Hellman key exchange you made afterwards. So this doesn't provide forward secrecy. But this is why you have to choose your parameters so that they provide forward secrecy. Combined encryption and authentication algorithm, authenticated encryption for data rather than serial encryption, authentication for based on AES. But we already mentioned this. So actual TLS 1.3 supports AES with GCM mode, which provides both authentication and encryption, or you can use ChaCha with the poly message authentication code. So this way it provides you authenticated encryption. So I already mentioned this when the TLS 1.3 were in progress, we had the Caesar competition. So I thought that the winner will be included here, but instead they chose these algorithms. HMAC uses SHA-256, or it says 234, but probably this is 334. Okay, cryptographic hash function. Another typo here. So TLS 1.3 handshake, one round trip time. It works like this. Client sends hello, but together it sends supported cipher suites, Diffie-Hellman key agreement protocol, and parameters. Okay, so here again you can, this is one of the downgrade attacks. You can force the server by saying that you have the older version and older ciphers. So you should configure your server in a good way so that you shouldn't accept any TLS version or any cipher that is actually outdated. So this TLS server TLS hello message chooses key agreement protocol, parameters, cipher suite, and server side certificate. Client checks server certificate, generates key, can now make application requests. So as you can see, this is a lot faster compared to previous runtime trips. Initial hello message contains encrypted application data, resuming earlier connection between client and server. Application data encrypted using resumption master secret from earlier connection. So if you're continue with an earlier connection, we have zero communication, right? Because here you have to wait for the cipher suites to be selected. Now, since you already have selected the ciphers and already have the secret keys, you can continue communicating without any further handshakes and so on. So this is the nice thing about TLS 1.3. But vulnerable to replay attacks, may be okay for get HTTP GET or client requests, not modifying server state. Okay.